the pandemic, but of course it's appropriate. Diane had referenced the this in I think on one of the Saturday webcasts. So there was the old story goes, I don't know if it's an oracle at Delos or it's the people of Delos. I've heard different versions. But let's say it's the people of Athens going to the oracle at Delphi or Delos, and they got a plague and they're asking the great oracle of wisdom. Now, you have to realize the oracle is not anything, I don't want to give the oracle too much credit. You know, it's kind of like asking the Federal Reserve, how do we solve the pandemic? But anyways, they came up with something, say double the size of your altar. So when the people of Athens came back, they asked the question, they told us to double the size of our altar. Like, who are these idiots? And Socrates said, no, actually, there may be something to this one, because you've lost a certain principle of scientific thought. You could say geometry. The problem is, and what we're going to take up today is this difference that I'm making now, which is the difference between the quality of principle of scientific thought versus what we've come to know as geometry. And that distinction is very important. And Socrates is making the distinction because they're getting flooded at the time by a kind of sophistry. We know this from Plato's dialogues. Dave Shavin can say much more on that, and does often, I'm sure, in the Plato classes. But this question of lowering the quality of thought of a people. People try to stay muted for now, if you can. But I do like people to unmute and say things. So, but the idea of lowering the quality of people's thought is clearly what empires do. That's what the Persians, you could say the Chaldeans, that's what they oftentimes are working to do, much like we see today with our culture. So Socrates recognized this. Now, Archytas is a unique figure. He's a close collaborator of Plato. And if I misstate anything, David or any other of the other kind of Greeks in the audience can say more. But it's funny, you know, this Archytas is from a town called Tarentum, which came up in the news just recently, because China wants to invest into a major R&D and industrial process in the town of Taranto today. Tarentum there, and what the Latin spelling. It's actually on the sole of the boot, on the very bottom. Yeah? Oh. So anyways, so this is a town of something like 300,000 people in this ancient Greek world, on the southern part of Italy, facing the Mediterranean, facing Libya, facing Egypt. There's not much left of it today, but Archytas was the political leader of the city. He was what they would call a tyrant or a dictator, but he was just the leader of the city. And what he develops, because the whole question, and you get this when you look up, you research this question, what you'll find is that people are putting it as, well, the challenge is, can you do it with a ruler and with a compass and straight edge? Is it a solvable problem? Like trisecting the angle, or a heptagon, a 7-sided polygon. And that's just bullshit in a certain sense, because yeah, those are fine, but we're not looking at this from the standpoint of geometry. Neither was Socrates, neither was Archytas. It's a question of a quality of scientific thought, of elevating a quality of scientific thought. There are much easier solutions, in some sense, easier solutions to the solving of the doubling of the cube. What Archytas provides is a demonstration of a quality of thinking. That's what's just so remarkable. Now, I think many people on the call have seen this. They've seen Bruce Director's many presentations. You've been confronted with this. But I don't, what we in discussions here, going back to late last year and then early this year, was a sense of looking at this problem that people hadn't really gone through and worked through the idea of it. It had been presented, it had been kind of plopped in your lap as some kind of profound thing. And the problem is you end up taking away as, wow, that's amazing. Archytas must have been an incredible genius. But you never really understood the thought as a natural extension of human creative thought. So then we had to figure out, well, how do we approach that? How do we think about it so that it actually is not simply just show you what Archytas did. That we actually have to kind of bring people into, you almost have to bring people into a way of thinking of classical Greece. And once you bring people into a quality of thinking of classical Greece, and to develop a language, because much of this is a language, even geometric proofs were just a kind of development of a language. It'd be like distinctions between verb tenses. You want to have those distinguished so that the mind can communicate more effectively or freely in the language of understanding the physical universe. We are going to do a couple of geometric proofs. And hopefully we can do it as creatively and playfully as possible. But the most important part is to get out of the kind of world that Euclid imposed. The kind of world that this cult, this kind of Aristotelian ideological cult imposed. And this is a rife political fight. I mean, it's a tense political fight to this day. And so we'll cover a little bit of that today. I think you'll get a better sense of what I'm meaning. It may seem esoteric now, but it'll get more clear. So we figured once we get the language and we get a quality of thinking of classical Greece, then we can move into how Archytas defined the problem. And you have a sense of why he defined it that way as part of the natural language that would come up. It's still unique, it's still a creative approach, but it should extend more naturally. Once we define the problem the way Archytas probably did, we'll understand then, we'll start to extend that and say, how do we get out of the problem that we're in? Because once we define the problem, we'll very quickly come to realize there's no way to solve it by that definition. And that's characteristic, right? You can define a problem from a certain standpoint that, though the problem can be identified clearly, cannot be resolved from that perspective or standpoint, from that system. You have to change the system. You have to change the way you're thinking. And geometry is fun because it kind of simplifies the rules a little bit. You know, we're not fully dealing with the physical universe. You're dealing with the creativity of the human mind. But we kind of simplified the physical universe to a certain kind of set of relationships. And so it kind of helps us to clarify the scientific process. Now, though what it doesn't do, and this is what Kepler and what physical science have become and demonstrate to us, more like what music also contributes, is that there's more an ambiguity to a true physical investigation of the universe. Yet the unique aspect of geometry, and I'm just kind of waxing here a little bit to give a context, is that it provides such clarity to your sense of knowing. So knowing something in the physical universe will never become maybe as distinct or sharp as knowing something geometrically. But it sets a watermark or a standard to the degree by which knowledge can be ascertained. And I put it that way because it was something that struck me when you look at Leibniz's writings on China. He has some section, and maybe I should pull it out so I'm not always paraphrasing this and then probably misquoting it to some degree. But from what I recall, Leibniz has this section where he, in regarding the Chinese were very, they marked with distinction, let's put it that way, the kind of precise knowledge. And if you've ever read Leibniz, if you read the Discourse on Metaphysics, he has all these kind of qualifications or degrees of knowing, precise, clear, and so on, kind of adjectives to describe the different levels of understanding or comprehending something. And the Chinese were struck by the clarity of knowing something. So, so that's what this kind of will provide us, I think, as a framework. Now, for a lot of people who have seen this before, and I know that this was the case with the team here, you know, it's been one of those things that people never thought they would get. They don't see themselves as mathematically inclined. It's always been presented as a beautiful solution. But what we found is if we take the time to go through this, and there's feedback and discussion, and we develop a language, that people are almost struck by how natural the hypothesis seems. And that's the question. Once it almost seems natural to you, the way Archytas is thinking, you know that your quality of thought has improved. And that's the joy of this. That's what makes this fun. Okay, so that's kind of my introduction. Now, let me make one. We're going to do a thought experiment today. And we're going to do and then kind of an investigation off of that thought experiment. So I send out an email, maybe not everyone might have gotten it or not, but if you have a ball, racquetball, tennis ball, an orange, some spherical-like object that you can draw on. And people might have done this experiment before. It's nothing too complex if you've looked at spherics or spherical geometry. But if you haven't, or you just want to kind of re-engage the questions, have a marker, a pen, some kind of spherical object if that's available. So that's what we're going to kind of do today and situate. And then if we have time, because I want to wrap up around, what, 8 o'clock? You know, with a little bit of time here and there, East Coast time. Okay, let me do one thing. So can people see that okay? Can I get thumbs up or thumbs down if you can't? Okay, good, great. I often think of this, the question of, say, doubling a square a certain way. And maybe I'll ask people to see if they have any hypotheses. If you were, if you had a young child, say 10, 11 years old, and blind, how would you communicate the doubling of the square to them? How would you communicate verbally to a blind child how a square can be doubled? Does anybody want to take a shot at it? See, now the thing is that the question that's now in your mind about having to do that, which, you know, invokes the kind of challenges that educating Helen Keller, but of course she couldn't hear either. But it provokes, in a sense, the imagination of why the doubling of the square is so important. And in terms of us to think about this, because you have to have some metric in your mind of what we're attempting to accomplish with this problem. And we haven't really defined the problem yet, but the important part is to think about it. You know, how do you describe that line? If you've captured what the square is in the mind of the child, how do you then capture that line? Now, no one has to answer it now, and I'll ask you probably later in another session. But there's a specific nature to that line. You can define that line physically. Versus if it was this line, that line's much more difficult to define. You'd almost say it's impossible to really define. However, the other line is not. Okay, so that just provokes something of a way of thinking. But if we do this effectively, if I do this effectively with your participation, you should be able to define in the mind, a young mind of a child, even who's blind. We had John Cavici on for the sessions we just did the last couple of months, so it was fun to have him on. And John's imagination is very good. If people don't know, John's a member for many years, but he's also blind. But you should be able to replicate with clarity in your own mind into the mind of the child that such things would be possible. So that's a fun challenge. Okay, so let's start with the mind experiment. I want everyone to think about, imagine yourself as a point in space. Now that might seem, degrading or something, but really, if right now you're operating, I just mean visually. So imagine visually that you're a point in space. Okay, now you can close one eye if you want to, but all that basically means is sit still, stand still, look out in front of you, and don't move much. Now, when you look out, I want you to take your finger and I want you to point to 3 distinct objects in your field of vision. Just point to 3 of them. Okay, just pick 3 points and find all 3. Now, if you had to describe those 3 points' relationship to each other, how many dimensions would it require? How many different kinds of motion would it require to say capture the relationship of those 3 points?
3.
Take it this way. Take the 3 points, start at the first one, and then either move horizontally or vertically only. So move left and right or up and down. And see if just by moving left and right and up and down, you can point to all 3 objects. That's fairly effective, right? Every point in your field of vision right now, you can point to, and all you're going to need is 2 different directions, left and right or up and down. Now, how many dimensions is the room you're in right now? What's the spatial dimensions of the room you're in? Is it just 2 dimensions? It's 3, right? Why did it only take 2 dimensions to describe all the various points in your field of vision? So the reason I'm asking this is it's similar to the question.
Can people mute
Okay, so
so they don't keep
this
popping up in the speakers area?
Huh?
If people are unmuted, they keep popping up anytime they breathe or something.
Oh, what you do is go to my video. Go to my video and go to the top right corner on the 3 dots and click on that and then pin my video.
Pin your video.
And that way you'll only see me even if other people are talking. Or you'll see the screen, see the whiteboard. So it gets at a funny paradox. So the point is that everything you're looking at right now in a 3-dimensional room, if you're fixed, if you're not moving, of course you do have some parallax, you have 2 different eyes, so there is a spatial dimension. You know, it's always the funny thing, if you have one eye closed and someone throws a ball at you, you won't be able to see the depth. It's a fun experiment as long as the ball's soft. But how do we get to 3 dimensions of space then? At that point, if we weren't moving, then 3-dimensional space seems entirely 2-dimensional. But then the question is it simply 3-dimensional space that allows me to move? So once you move, if you move your chair or you walk around in the room, all of a sudden now things that were not visible to you before, like for example, the camera is blocking a corner of the name of the television. When I move over, I can see the name of the television. That wasn't there before. And the reason I'm raising this is the question is what's actually ontological about the world we're living in? Is it simply the spatial parameters built up? Did space come first, then matter, then motion? Or are even the constructs of space itself, the so-called spatial dimensions, are they intrinsically dependent on a higher characteristic? Like if I'm not able to move, then 3 dimensions quickly becomes 2. It's my ability to move to then identify 3 dimensions, but where did my ability to move come from? Where did that notion of action or motion come from? And I raise this because there's this notion of spherics. It's similar to the experiment you just did by pointing to 3 spots. It's why the nighttime sky always appears spherical. Because if you're essentially fixed in a point in space, everything around you is practically as the same distance away. There was no spatial depth to one point in space in relationship to all others. Everything was infinitely far away if one's not moving. It becomes like a spherical projection of the nighttime stars. This quality of thinking, this sense of so-called space as an investigation, is an artificial construct. That's not what we're investigating. We're investigating the ability of the mind to know the physical universe. And that comes in with something primary or prior to just spatial dimensions, right? Because spatial dimensions, Euclidean space, Newtonian space, these things they become implanted in our culture, but they're not intrinsic to the way the human mind would naturally think about the physical universe. That you can quickly use a kind of childlike experiment to find out that there's something different. This goes back to something Lynn always referenced, which is a triply connected physical process, or triply connected circular action. People are familiar with this, I think, but I'll just draw it as an example. So if we take there's our first level of circular action. If I take another one, that's horizontal to the vertical plane, then I've got two, and I've defined 2 points. If I take another one, and we start to see that the remnants of so-called or aspects of three-dimensional space are residues of a quality of action, and that the most clear action would be that of circular. And I think most people are probably familiar with that. Megan addressed it in the economics class. But what we want to do is look at how the Greeks were thinking. And we'll kind of unfold this a little bit more as we go through. We'll get more into the geometry. This is probably the most just straight talking I'm going to do, unless we get into certain questions at some points. But now I want people to take out, if they have a ball and a marker, to take that out. Because what this gets into then is, how do we think about measuring physical space? Because that's, in some sense, what this notion of the language of geometry, how do we measure the physical universe? How do we grasp some of these characteristics? The motions of the stars. You know, it was a great challenge to take the spherical stars and map them onto a flat piece of paper. That's an intrinsically difficult challenge. If you're going to map certain stars and yet they're spherically projected and you've got to do something that's on a flat plane, there's distortions the way that those things are going to map. It's like trying to take an orange peel and make it flat. There's intrinsic problems. So now if you've got your sphere, you've got your ball, and if I draw something out of sight or it's hard to see, just someone shout it out. Okay, so there's your ball of sorts. Your sphere, your orange, whatever. Start from the top of the ball or orange and draw halfway down. So start up here and draw down to the equator. When you get to the equator, I guess if you're traveling down, make a right-hand turn and go over to the edge of the ball over here. And then when you get to the edge of the ball, so that you're kind of at the next equator, draw up all the way to the top. Okay, now does anybody want to say, here's the question, here's the nature of my questions. If you totally know the answer, then don't speak necessarily. let's see if we have people that might have conjectures, because it's that dialogue which we all know is rich to finding out what is true and how you're thinking. But can anybody tell me what the nature of this angle is? Like, how big is that angle? How would you describe that angle if you could? Does anybody have an answer or a suggestion?
Yeah, Mike,
Yeah,
it's really big.
really big? Is that what you
Yeah.
said?
That's my scientific answer. I'm on a serious.
Well, here's okay. Let's just take it up as a dialogue. That's good. That's good. So if you take a right-hand turn, Bronx has probably got a decent grid. If you take a right-hand turn, what's the angle you're taking on your right-hand turn?
Well, 90 degrees.
Okay, good, great. So let's say this is 90 degrees. Is the Bronx entirely flat?
No, it's actually the highest elevated out of all of New York City. It's got the most hills.
Okay, so let's say it's a 90-degree turn. What about this angle? This is the same thing, right? We came to this point and we took another 90-degree angle, right?
Well, yeah, but it doesn't look that way. Okay, yes.
Well, what about if I just went straight like that? What if if I come this way and then I come to this point and then I kept, that angle right there is 90, right?
Yes.
Right. Well, so is the angle, it just tends to curve a little bit. And then this angle, if we come up to it, we're going to find that that's also 90 degrees. Okay, so that means this triangle has how many, what's the size of the triangle? How many degrees of angles does it have? If you took all three angles and combined them, how many degrees would it have?
180.
No.
270.
I've got 90, 90.
Oh, 270. 270. Sorry.
I've got 270 degrees. Okay, but Jose made the point implicitly, right? He assumed that if it's a triangle, it's going to have 180 degrees. How many people think that's really kind of amazing? Probably not many. Yeah, it's neat. It's neat. But that makes sense. If I redraw it, you'll get this. It's kind of like, you'll see where I'm going. Just hang with me. Okay, so here's our sphere again. And people know that this is our equator here. When these lines of longitude come down all the way from the top, the North Pole to the South Pole, like on the sphere, when they cross the equator, they all cross at 90 degrees. Much like what we drew here, right? We went down from the North Pole down to the equator and then hung a right turn. Now,
could I ask, does that happen even if they're not equidistant, along the horizontal plane or whatever you call that, the equator? Does it happen if they're equidistant only, or any width between?
Well,
them?
if they're going all the way around this, if they're touching the pole of the sphere, if they're one of these big circles, and they're intersecting another great circle, then it's going to be 90 degrees. Halfway, if they're intersecting halfway down the sphere. I should probably be more specific. They don't have to be, the distance isn't a matter, it's the relationship between the two. If you're on a great circle and you, see how this works. It's always fun when questions come up and I've got to rethink. Okay, yeah, we'll just leave it there. If there's more questions, we'll get to it.
Any great circle that goes through the top of the sphere is going to intersect the equator at 90.
Yeah, that's right. I'm just trying to think of another great circle intersected it. No, it wouldn't always be. Yeah, it's always the equator to that great circle.
Or anything parallel to the equator.
Or anything parallel to the equator. Yeah.
All the
Yeah,
latitude.
that's true. Yeah. Okay, good. Yeah, that's useful. Okay, now people might recognize this. We're kind of building up to a point, so like I said, hang with me. Does anybody want to describe the relationship of this line to this line A to this line B? Based on the fact that they've been intersected by another line with the same angle? Come on, I know someone's got it. It's not.
They're parallel?
Okay, all right. So they're parallel lines. It's one of the basic things they teach you in high school geometry. They make it seem like it's totally true. You don't have any idea why it's important. But wouldn't you say that these two lines here, this line here, and this line here, are also intersected by a third line and have the same angle? Now, most people are familiar with this. I think a lot of people in the class are familiar with this polemic. It was said that these two lines, if intersected by a third, would never touch. They would just go on infinitely. They would never intersect, that parallel lines never intersect. And yet here we have a very simple case of two lines which intersected by a third, and yet at the poles, they both touch. Now, can anybody give me an explanation why these two lines would never touch? Or does anybody have an idea why these two lines would never touch? And why these two lines, why those two lines also intersected by a third line, but they both touch. They touch at the North Pole and the South Pole. So anybody that doesn't maybe remember the answer have an idea?
Is it because the top picture, that's the three-dimensional space, and the picture below is two-dimensional?
What do you mean by two-dimensional?
That there's only two dimensions, that it can only go it's only going left and right. And
Well, remember when we were pointing at the three objects that we saw in our field of vision, or if we were drawing the triangle on the sphere, we went right and then right again. We never went out into space or back into space. We never used a third dimension.
Right. Oh, sorry. Right. I mean, the picture below, it's flat. It's completely flat, whereas the top, it's a curved surface.
Right. Okay, good. Yeah, that's the difference. So this is flat and this is curved. Does anybody not understand what Kynan was referencing? Is anybody confused by that idea? Anybody want me to say more on it or try to investigate it more?
Mike, are you saying there's a difference between a curved surface and three-dimensional space?
Well, yeah. Yeah, that would be true.
Yeah. So question. Well, just on the triangle on the on the sphere. I mean, is it even a triangle anymore? You did catch me on, implicitly believing that triangles are 180 degrees. And so I responded off instinct without thinking. Wasn't until I caught myself. But see, now that kind of perplexes me, because I tried to draw a 90 degree, every angle 90 degree on my piece of paper. All I got was a square. So does that mean that this is not a triangle, but rather something else? Is there a name for a triangle that exists on a curved surface that has now 270 degrees?
Well, the question is, does maybe the size of your triangle tell you something about the surface that you're dealing with? So if you define a triangle, it's 3 sides, 3 lines drawn. You could say 3 straight lines drawn that intersect to make, with 3 distinct angles. Well, then that fits. We just went straight down, straight to the right, and then straight right again. Now, the funny part is that it brought us back to where we started. On a flat surface, it doesn't always do that. It never does that on a flat surface. So there's a difference, right? There's a difference when you're operating on a sphere and when you're operating on a flat plane. Did anybody want to say more, or want me to say more on that?
Yes.
You want to try to tell me what you think I should say, or like what direction you want me to go?
No, not in particular.
I have
Just
a
say more.
question.
Well, I have a question actually,
Yeah.
and maybe I don't know, maybe this isn't really relevant for what you're going to go through, but what is the difference between the angle that the latitudinal circles make with the great circles?
Oh, these questions here, yeah. The 90-degree angle.
Yeah. Is that 90 degrees?
Yeah. Yeah, I think it is. Yeah.
Okay, and then the other question is, which came earlier, is there a difference between curved surfaces and 3-dimensional space?
Right. Okay, so, well, that's why we started off with there's a big difference, isn't there? And we'll find that there's a big difference in dealing with the nature of the problem of doubling a cube. Because once you're actually dealing with 3-dimensional space, so you're in a 3-dimensional room in the sense that it's got a length, a width, and then a height. Yet if you're fixed in that 3-dimensional space, so we haven't added, you could say you haven't added the 4th dimension of time, you haven't added any motion or action, you're just in that 3-dimensional space, that 3-dimensional space is presented to you as 2-dimensional. So when you're going to deal with 3-dimensional space, it implies for us, if I'm going to now deal with a 3-dimensional room, I have to be moving in it. But there's nothing about those so-called spatial dimensions which provide motion. And so it becomes a paradox. So there's a big difference between something like a sphere, which basically 3-dimensional space looks like. If I'm a static object, it's like looking at the nighttime sky. I can point to all different kinds of objects as if they're independent stars. But I couldn't tell you if I'm a fixed point in space without the parallax of 2 eyes. I certainly would have no idea the depth distance of anything. I wouldn't know if anything's behind another or in front of another. Hence the challenges of, deep astronomy. So a 2-dimensional surface can be any surface. We had the whole You know, you have the old flying carpet. As strange as an object as you can imagine in space, with all kinds of strange contours, curves, dimples. Wherever I'm on this surface, I can move straight ahead, and I can move left and right, and I can get to any point on the surface. So when we talk about dimensions, if the dimensions are of a necessary characteristic, you could make more dimensions if you wanted to. It just would make everything more sloppy and complicated. So there's an efficiency to how we would capture dimensionality. Once you actually go to another dimension, it is a more complicated system by its nature. And so this kind of gets at why we're doing all of this. Because though it's fun, these are fun questions. It's not just to have there's something beyond just the philosophical nature of this. This question of a relationship of physical action, of knowability, of dimensionality. The Greeks, their Egyptian predecessors, you know, Archytas is part of this kind of Pythagorean network of sorts. They thought in a different kind of language. They recognized that there would be differences between something like a spherical surface where all parallel lines meet and a flat surface. Because only when you recognize flatness here, that we're assuming this plane to be flat, infinitely outwards, that then these lines would never meet. Parallel lines never meet. If you can find somebody that says that, you'll have a very good time changing the way they entirely think about the universe, especially if they're some sort of physicist or scientist. Now, they might think you're just doing a trick on them, but here's the difference. These ancient Greeks, this classical Greek culture, thought in these questions of action and motion. The imposition of this Euclidean approach, the logical method of Aristotle, was something imposed in the decline and fall of classical Greek thought. It's not for nearly 2,000 years that a gentleman named Abraham Kästner, a German, in essence a student of Leibniz, he recognized that this, what they call the parallel postulate, that two lines intersected by a third that meet at right angles never intersect. Kästner realized, wait a minute, that's only true if we assume flatness. Now, what does that mean? It means if we think of lines as of action in the physical universe, then the surface those lines are acting on are kind of like the underlying principles or underlying characteristics of the physical universe. And if we're assuming now flatness to be the characteristic of space, that you start at a certain point and it goes out infinitely the same way the entire time, then you're assuming something about the physical universe as a whole. And Kästner said, that seems to be a problem. You know, Bruce, we had that discussion of Brunelleschi's dome when it was referenced by Trump at that speech in Switzerland at Davos. Brunelleschi didn't think this way. He wasn't brainwashed. If you look at Kepler's New Astronomy, he spends most of the early part of the book thrashing the Aristotelian Euclidean approach. But Kästner in around 1750 finally realizes this is true. He realizes this difference, the difference that Kynan and everyone else, I think right now, should feel comfortable making the distinction of. That parallel lines on this surface intersect, they don't on this. You're assuming something about the underlying nature of something. Kestner said, we've got to make that clear. So Kestner had two students, Carl Gauss and this guy, Bolyai. Now Gauss knew it, but he never said it. The reason he never said it is because he could have been killed if he said it. Kestner never said it because he could have been killed. Think about this. It's like a childhood experiment that you should have done when you were in the 3rd grade. It's a very playful investigation of the physical universe in a simplified form. But they were going to be killed if they didn't say it. Or killed if they said it. It wasn't until 1850 where Bernard Riemann finally is able to say it and say the implications. They came up, other people came out and said you could have spherical geometry, you could have negatively curved geometry. And we could maybe get into that if people at some point or now or today we can see. But they developed, there's a spherical geometry, Euclid does flat geometry, we could set up a system of spherical geometry. So like, Jose, you recognized, well now, some triangles on a sphere have 270 degrees. If we didn't go all the way over, if we only went right here, it would have less. It would have 90 plus 90 plus 30. So this triangle here would only have 210 degrees. So the nature of the triangle, how many angles it has, tells you something about how big it is on a sphere. That's just one example of, say, spherical geometry. Versus on a flat plane, every triangle will have 180 degrees. No matter how you draw that triangle, it's always got 180 degrees. So Riemann says, okay, not only is that interesting, it causes us to reflect upon how we think about the physical universe. He says this in 1850. So it's public for only 50 years. The classical Greeks knew it. We're talking 500, 600, 500, 400 BC. This is general knowledge to a scientific literati. The Pythagorean networks, the Platonic networks, the Platonic Academy, they're thinking this way. At some point around 300 BC, a whole different system is imposed. It lasts for nearly 2,000 years as a system of thought about the physical universe. A guy finally realizes it. He can't say it, it's so deadly he'd be killed. It's not for 100 years and 2 generations of students later that finally can say, we're thinking about the physical universe entirely wrong based on these kinds of questions. Mankind goes through one of the most rapid developments over the next century, from 1850, you could say, until, say, 1970, a little bit more than a century. We go from horses, we go to a lifespan of like, we go to atomic science, we go to rocketry, landing men and men on the moon, nuclear energy, and largely based on discoveries from 1850 to 1900. So in a 50-year time span, all the major discoveries, the rocket scientists, the people that make the breakthroughs in rocketry that decide they're going to go to the moon, the technology of 1850 is not much different than the technology of, and there are experiments, there's electrical experiments, there's railroads getting built, but if you go back to 1750, when Abraham Kestner develops this, the technology of 1750 is not that much more advanced than 400 BC or 350 BC. So for 2,000 years, technology is generally static. From 1850 to 1900, all of the fundamental core breakthroughs in scientific thought occur in the wake of Riemann demonstrating the implications of these questions. What happens in 1903? Bertrand Russell comes out and says very clearly, Euclid and Aristotle have failed. They didn't provide perfectly closed logical systems. They didn't create systems without axiomatic assumptions, like the assumption of flat space. So Russell says, let's develop an entirely new language with no assumptions and perfectly contained. It can capture everything in the universe and there's no hidden assumptions. And he writes this massive work with this guy, Alfred Whitehead, both total British agents. I don't know if either of them ever even wrote this thing. They might have gotten a couple of kind of strange savants to spend their time doing this. They may have been involved. It's really hard to say. Probably 5 people in the world have ever even read much of the book. I think it takes something like, you have to get into the second half of the second volume. So you have like 1,000-page volumes. I think there's 4 and they never wrote the 5th. You've got to get into the second volume halfway through before you finally understand why 1 + 1 = 2. Okay, that's literally what Russell does. But because this becomes such a dominant way of thinking, it's insanity. All of these questions are then immediately taken away. That quality of thought that Riemann introduced, going back to classical Greece, was obliterated. How do I know that? Because most people, you never got this in geometry. You'd have to already become a kind of a math geek in advanced areas in college before you started to get these clear geometric distinctions that a 3rd grader could understand and have fun investigating. What you got instead was algebra. We'll actually explore it, we'll actually come upon a certain characteristic of where algebra came from, which it's a useful tool, but you were largely trained. Our entire culture, our entire scientific community is trained on algebra. Why? Because of Bertrand Russell's book, or volume of logical insanity. Because algebra is perfect, so they say. It was proven later to be a complete fraud. It can't include everything in the universe, it's not true, and it does have hidden assumptions. But the whole book is just of a degree of insanity far beyond Euclid. You see it today with the pandemic, right? Every doctor came out of authority and said, here's what's going to happen with the pandemic. What were they doing? Running a computer model, a series of algebraic relationships. You put in certain data, you get certain results. There was no consideration of the underlying characteristics. The underlying characteristic of the United States has psychological features, infrastructure questions. That's what we're dealing with. And you see those psychological features manipulated constantly. You get the overreach of stupid Democrats, the craziness of certain Republicans or conservatives. And those things are manipulated because of underlying characteristics, because a bunch of people who said they're authorities came out and said, we're authorities because our computer models say this is going to happen. And then a week later they say, oh, we've revised that. It's absolutely a different idea. You can't do that unless you want to give people no confidence in scientific thought. You want to take away people's confidence of scientific thought, say apocalyptic doom is going to happen on the earth if we keep emitting carbon. Why? Because computer linear models tell us that's what's going to happen. And you wear down a confidence in a population in the ability of mankind to know the universe from a higher scientific level. And so as funny as this, as simple as this seems, you'd never think that the person who really came to realize it in the modern era was unable to say it throughout his entire life. And when Riemann said it, Karl Gauss, Abraham Kästner's student, was in the audience. And Gauss was grinning ear to ear, in essence. Maybe in his mind, maybe outwards. because he knew he had finally taken the veil down. We're now getting to look at what are the underlying characteristics, the unseen characteristics of the physical universe. It's those unseen characteristics which is what we're investigating in scientific thought. What are the undergirding principles of the phenomena that I see? What's the underlying characteristic of the shadows I perceive? From a higher scientific standpoint, it was this question of geometry which is the basis of Einstein's general relativity. That's one place any student would get it today. Go look at Einstein's writings on relativity, and you'll find a chapter entirely on Gaussian curvature, the difference between a flat surface and a curved one. But never does anyone mention that it was known for 100 years, finally released. The level of breakthroughs of scientific thought were so miracle. We're still living off of their legacy today. And yet within 50 years, the book was closed and a more even harsh system of brainwashing was imposed. Because you have to realize that's where we are, and that the classical Greeks, they thought this way. They thought about these underlying relationships. And if we think that way, what Lynn would often reference, the German term of Kraft, or power, the powers, higher powers. You talk about algebraic powers, you know, x squared, x cubed, x to the fourth, but there's a notion of power of dimensions. And you have to be willing to recognize those distinctions and differences. Okay, so that's my philosophical introduction to how we want to approach this. What time is it? 4:30 my time. Okay, so we got about half an hour. So why don't we see if there's any questions or thoughts on that, and then we'll jump in to start defining the problem of doubling the cube.
I have a question on your, what you're saying about what happened in the 19th century with Kessler and Gauss and Riemann. I know they made major breakthroughs, but I can't believe that the Renaissance, with all of the developments in art and architecture and ocean voyages and discovery, was based on Euclidean geometry, which is what you seem to.
Oh no, I mean no breakthrough is based on it, but as a system of thought. Right, as a method of thought to identify what. If they think about Kepler's writings, Kepler has to trash and deconstruct all of the fraud of Aristotelian Ptolemaic thinking in the New Astronomy. And when he writes his harmonies, besides the Rosicrucians and other networks around King James in England, the book is largely rejected. And Kepler says, I don't care if anyone ever realizes this for 500 years. I know that I've just grasped into the heavens, in essence. So no, of course, no, Brunelleschi didn't think Euclidean. He couldn't have. But Brunelleschi didn't make his quality of thinking conscious to others. He demonstrates it's possible. He inspires it and provokes it in others with a passion of what's possible, that the impossible can be done. But the intrinsic point is that Kessler knows that what he is saying is so threatening to the mathematical priesthood. Remember, think of Napoleon. Napoleon considered himself a mathematician. He loved Laplace, Lagrange, D'Alembert. Later you get Cauchy and others. They were all situated. A lot of mathematics and algebra come out of gambling. All of statistical analysis comes out of gambling. And what Kessler is about to introduce is the kind of thinking that was revived by Plato in the Renaissance. What Brunelleschi provoked, what Cusa was reviving, the way Kepler thought. We're now making the way Kepler's genius, we're now making it a knowable kind of approach. Because what does Kepler do? He asks, not just what do I see? He says, I want to first document accurately what we're seeing, which he does, and removes errors and observations. But he wants to know, what's the underlying system? What are the underlying principles guiding what we're perceiving? Not simply can I forecast where a planet will be on a certain day, which was the game that the priesthood played at that time, like watching the stock market. So So yeah, I'm not saying that one thing, but hopefully what I am saying is more clear. I mean, it's so powerful that Bertrand Russell, the British have to destroy it within 50 years. Yeah, go ahead.
I was just going to ask, I was thinking about who are the powers that are going to kill these people. And of course, the Inquisition comes to mind, but it's sort of, I know Cantor had to, meet with the church to try to clarify the truth of what he was saying. But could you elaborate a little bit more about the enforcement operation against that kind
Yeah,
of?
just go back and look at what Gauss was dealing with the French Revolution and the Napoleonic era. I mean, many people, I have to recall some of the history, but take people like Niels Heinrich Abel or Galois, who were targeted. Even Riemann himself was largely targeted. And it's like, look at John Keats. I mean, I know Dan knows this case. Look at John Keats. He was targeted. That's how political operations work against great geniuses. So it was that kind of threat. They just knew how dangerous these ideas were. And so it just gives a sense, because the context I'm wanting to present is the political intensity of these ideas. And if we just look at them as interesting philosophically, it's fun. I mean, it's absolutely enjoyable. But there's also a context, and the context is almost remarkable. When I saw Bertrand Russell say this in 1903, I was stunned. And you realize what Kestner had introduced, but never really developed. Gauss never made his writings public on these questions until much later. So it's, there's just a kind of political intensity, and the fact of the classical Greeks thought a different way. And that's what we want to try to grasp from Archytas. Okay, so are there any other thoughts or maybe even reflections that people might have based on what we've gone through?
Michael, there's a question in the chat from Jessica.
Uh-huh.
I don't know if she wants to ask it or if she can.
Sure. Hi, Michael.
Hi.
I asked a question earlier when we were talking about the difference between the three-dimensional sphere versus the two-dimensional flat plane, and I asked, and you were talking about the point as the observer, and so I asked, doesn't our interaction with the fourth dimensional time give our 2D visual perception of reality its manifested 3D properties?
Yeah, I mean, the question is that 3 dimensions only arise when you provide the fourth dimension of motion, if we want to describe it that way. There's a problem describing it that way. There's a guy named Minkowski that tried to say what Einstein was introducing was this fourth dimension of time. And so then you get into, and you can map all of the special relativity that way. I just say that to kind of give a sense that you're kind of building up from the bottom. You're starting with the idea of spatial dimensions first, and then you're building up to second, third, and fourth. But the fourth dimension of motion is so drastically different than just simply a dimension of spatial extension, right? An extension of space doesn't imply that you can move along it. Motion has a totally different characteristic than simply extension. So I think we have to be careful of building upwards. What we might want to do is invert the whole thing and say, let's actually start with the principles of motion. Not of motion itself, but those things, those aspects of the universe which enable motion to occur. And in that regard, the sphere and the plane, and this is the common dissonance in the mind, because the sphere is not three-dimensional. You could have a three-dimensional space that was spherical, but if you're operating only on the surface of the sphere, then there's only ever 2 dimensions. that I need to get to any location. Just like if I had right, there's multiple ways I can get from this point to that point. I don't know, can people see those other lines? I'm betting you can't. You can? Oh, okay, okay, yeah. So I think people get the idea. You can see where my hand was going too. So there's multiple different ways you can get to the 2 points, but you never have to use anything but a 2-dimensional grid. The same is true on the sphere. I could pick any point on the sphere to go from the North Pole to any point. And I would, if I traveled only along the surface of the sphere, I could just take 2 different directionalities, up and down along the sphere and left and right. Now those things are different on a sphere than they are on a flat plane. Right? The ones on the sphere become circles. These are infinite lines, but both of them are 2 dimensions. And that's the funny irony of, and that's kind of how they've got us a little bit brainwashed. Because we're assuming space to always be flat as a characteristic. And so it's something that this is something you can work on for a long time. There's a lot of work we can do in this direction. And that's partly what Archytas's quality of thinking will contribute to, so that we can really understand the kind of universe Einstein was thinking of. Not in crazy mathematical terms, but in really a kind of a physically insightful way. Does that help answer your question, or do you want to ask?
Yes, no, definitely. That was really great.
Okay, good.
I do have one more. I don't know if that's okay.
Yeah, go ahead.
One more question. In reference to when you were talking about the second time the hammer was coming down, I guess after Einstein's discoveries with Bertrand Russell, is that more so? I'm just interested to know how you would describe that situation in terms of, is that just something that halts the progression of the thinking, or something a little more concrete? Sorry,
Well,
that wasn't really clear, but.
No, it's totally clear. So, Michal, will you just turn it down a little bit?
The volume?
Yeah. So the, it's a funny thinking, but think about the role of scientists in our society, right? Everybody has some sense of lens economics. We think about the role of scientists and what they provide. They're a very unique aspect to a human society. Now, a lot of people that consider themselves scientists, I don't know if they really meet the beauty and profoundness of the word. Just because you do art, does that make you an artist? Right? Just because you're involved in so-called scientific or physical research, are you a scientist? But the profound role that scientists play, to think about the future, to imagine it, and to see how we can develop into it with new discoveries, new ideas about how the physical universe works. So if you're an empire, you've got to do a couple of things. If you want to stop population growth, human development, you've got to brainwash your scientists. And that's certainly what Russell and Whitehead are out to do. Whitehead was a well-known kind of Cambridge philosopher. And you get people like John Dewey out of this network. And the point is not to drop a lot of names, but to say that this network targets specifically, first, educational philosophy. How do we educate young people? That's what Russell and Whitehead and Dewey and others are specifically targeting. And then they look at mass propaganda, which becomes culture, entertainment, music. And of course, they're wanting to eradicate that same quality of classical culture. because Beethoven intrinsically understands these questions. And he's constantly looking for new insights into the physical universe. He's not accepting assumptions about what music is. Whereas others merely compose based on a formula. And it loses, it doesn't grip the mind. It doesn't inspire the mind. So it's really an intellectual fight. And it's why I wanted to make the point, simply because these ideas, as simple and as childlike as they are, as shocking as it is, these really threaten our enemy. They really threaten our enemy. It shows you how incapable they really are in terms of thought. If it takes them a volume and a half to get to 1 + 1 = 2, we've got great intellectual advantage if we master this kind of thinking. Okay, is there any other thoughts? That was great. I appreciate those questions.
Hi, I just have a very short reflection, Michael.
Yeah.
Just thank you again for this, very short and, as you mentioned, simple experiment. As I was going through, I was like wondering, why didn't I learn this in my geometry class in high school? It's so simple, but at the same time, it just completely changes how I think about the world, about how, our space-time and how it's constructed. And that when you mentioned that the Greeks, the classical Greeks, they had this knowledge, and that, was lost for, however long, 2,000 years, when Kessner and Gauss finally discovered it. It really made me think about, like, wow, they were much more advanced than we were, despite, they were much more advanced in how they thought, despite, how different our societies may have been, or what different technologies we may have had at the time. So yeah, it's a really wonderful class, and yeah, thank you very much.
Oh, sure. Yeah, no, it's my pleasure. It's nice to have you guys on and to be able to do this. So, okay, given that, why don't we take what we've just done on a more philosophical and historical level and just now apply it to the problem as it's going to exist. Now, let me give a certain, one of the things that comes up is that we can sometimes take these mathematical investigations or geometric investigations, and we can try to philosophically extrapolate prematurely. So though it's been fun to investigate this, as we actually dive into the problem, what I've noticed is that sometimes people will get overwhelmed by thinking that they've got to draw these big general conclusions. And this may have been more with the last group that I worked with, because every dynamic's a little different. But I would always encourage people, if you feel like if it's getting overwhelming, that you're not able to hold it all together, don't try to philosophically generalize it more. Actually, just go back to the very simple aspects that are concrete and knowable. Because we're going to follow a very narrow path of investigation so that you can actually unfold the composition of Archytas. And it very much is a composition. But we don't want to necessarily try to expand it. Now, that might be for more people with more experience with this, with the problem. But I just say that as an encouragement, that if you start to get overwhelmed, just go back to the very simple questions. And if possible, just go ahead and raise questions so that you can kind of get back to the knowable characteristics, the things that are just about how do we follow this argument that Archytas implicitly gives. We don't have his argument. We have his creation. We have his composition. But I think you'll find that we can effectively reconstruct it. Okay, that all being said, that's my caveat. I'm going to erase the board, and then we're going to just define the problem. Okay, so there's probably a couple of things we want to do. let's do the fun thing. I'm assuming everyone's doubled a square. So when you present, because everyone's also probably done this, when you present to someone how to double a square, what's one of the first things people say? Just shoot it out, whoever wants to.
Put a square next to it.
Right, okay. So this question, right? That's what everybody says. Okay, and then eventually, you know, the Mino dialogue approach, you say, well, cut this square in half, and we double the square. Okay, so then if you're in the field or you're working with someone, and you say, okay, well, what about doubling the cube? How would you double a cube? What's the first thing that, what's something that they say now that they've doubled the square?
Take the diagonal.
Take the diagonal, right. Can somebody describe for me what the diagonal of a cube would be?
So you'd go from, I guess, that bottom left corner to the top right back corner. Yeah.
Okay, I'm gonna do the other one just because it's easier to draw.
Okay.
But that's the right idea, yeah. Okay, so I'm going back top left to lower front right. Okay. So that's it's just a fun experiment to do. Now, does anybody, and you can, I'll say this is the homework. If there's any homework today, this would be the homework, just like a fun thing to play around with. If you haven't yet defined how long that line is, try to figure out what the actual length of that line is. And it will tell you a little bit about the problem we're going to run into. Okay. Any questions on that? Okay, I'll try to bring it up next time, see if anybody figured it out.
There's a comment in the chat from Brandon who says there's two types of diagonals in a cube. Which I think that goes towards how you actually calculate it.
Right.
It has something to do with it.
I think he's right. Okay. Does anybody want a hint or anything, or are people good on that question? All right, good. So we'll come back to that. That's something that will just be part of, because we're diving into the problem, and so now we kind of have to flush out a little bit more details. We'll do constructions. We're going to do some geometric proofs. We probably should prove the Pythagorean theorem in some way. Since there's about 300 of them, I don't think showing one of them will be too problematic. We should probably prove that there's 180 degrees in a triangle. And there's one other proof that we should probably deal with. So those are some of the details, but let's just define the problem in the most simplified way. Let's start with a line. Why does this keep changing? It must be crazy. Okay. If I want to double the length of a line, how would you, if you wanted to double the length of a line, how would you do it? Anybody have an idea? Anybody have a way of thinking about it?
Rotate it around perpendicular to the board.
Okay. Like that?
Well, that's one way, yeah.
Okay, that'll work. Okay, so, and we can double the line, and we can, if we want to double this line, we could do that, and we could just do the same thing. And if we wanted to double that line, we could do the same thing. It's a nice linear process of doubling a line. Okay, now what if we add a dimension and we do a square? How do we double a square? Can we do the same thing? Well, that's kind of the fun part of that experiment. You can do it, but it doesn't give you another square. So the question of how are we dealing with the square changes from just a line. We've added an additional dimension. And so the approach has to change. The way of thinking has to change. Let's look at then a process of squares. We start with one square. We know that with two squares, we get a rectangle. And then we know if we go to three squares, well, if we double one square, we get two. If we double two squares, then we get four. So, and this is something that comes up in terms of, you can ask, what are the square numbers? What are the triangle numbers? If we did triangle numbers, you could do 1, 3, 6. What would be the next one? Anybody know?
10?
Yeah. So if we did squares, what's the next number that's a square?
9.
9. Right, and we can do the next one. It'd be 4 by 4. $16. But this is useful. You can use this as kind of a way of thinking about it because we're talking about doubling, right? That's intrinsically the challenge to the Athenians was, can you double the size of your altar? Can you double the size of the cube? So in some ways, we've kind of taken the broad historical questions of thought. We're now coming down to a very specific problem. Well, what happens with a cube? Okay. So with a cube, we start with one cube. We double it to 2. We double that to 4. But we're still not at a cube yet. We have to double it a third time. So you start with one cube. You get to 2. You get to 4. And then you get to 8. So in the line, we could double as much as we wanted to. And every time we doubled, it was always a line. With the square, we had to double it twice. In some sense, it has a relationship to the dimensions. Every time you double once, it stays a line. It's only one dimension. With the square, you're getting a doubling every 2 times, where you're back to a square as a characteristic. But with the cube, you've got something differently happening. But there's an actual doubling 3 times as a characteristic. Okay, so that's probably pretty straightforward. Does anybody have any questions on that? We'll probably come back to it. And I have more to say, but are there any questions right now? Okay. Okay, so then what are we talking about? Well, we know we can create a cube of 8. How long is the side of a cube of 8? Does anybody want to answer?
2.
2. Okay, good. All right, so the side of this cube is a length of 2. And the side of a cube of 1 is 1. Well, the challenge is, can we find the length of a line that gives us a cube of 2? What's the side? What's the side of a cube? How long is that length? That when we construct a cube out of it would give us a volume of 2, much like the way that this line, when made out into a square, gives us a square double the area. So the question comes down to, how do we define a certain length of a certain line? And yet that line has to have the power to build something of 3 dimensions, not simply 2 dimensions. And that's the challenge that we've got. You're going to find that this relationship, 1, 2, 4, and 8, is going to come back. And we're going to, what time is it? Yeah, it's going to come back into a certain characteristic. Does anybody want to, let me do one other thing, because I think it'll be important to kind of situate where we're going to go next time. And then we'll see if there's any questions, and then we'll just cut for the day, since I know there's people have more things to do tonight. So what we're doing right now is kind of getting into the nitty-gritty of the language that would have been, Archytas would have worked with very naturally. The idea of triangle numbers, square numbers, the kind of relationships of, say, cubes, that they would have kind of intrinsically investigated these things. It would have been part of their scientific research. It would have been part of their educational program for their young children, if they were part of Pythagorean networks. It would be how they would educate. You know, you think of Plato's Meno dialogue. Plato's showing this is how you educate a child, even a slave boy. This is how you educate them. It's part of the intrinsic culture of this classical outlook. And so in some sense, if you don't have to memorize anything, you kind of want to just kind of proceed with it, a sense that there's an investigation. We're kind of getting away of how they might have thought. Now, if people haven't done this, it's certainly fun to do. Let me, I don't want to be relegated to the side of the board. I'm going to erase all of this. Anybody have any objections to that? Okay. And this may seem a little bit tedious to some, but in general, I think it's the best way to help make sure that we have a good footing. Because what happens is once you get into the Archytas discussion, if we don't have a real thorough relationship to the language, then all of a sudden you feel like you're just treading water. If people haven't done this, it's fun to do. If we start with the square, and you would have to take a bunch of poster board, tape them together, and put them on the floor. I think, Michelle, were you there when we did this in Los Angeles? You might have been. And just keep doubling the next square. Okay, so this length is 1. What's the length of this line here?
Square root of 2.
Yeah, square root of 2. Okay, how about the length of this line?
It's 2.
What about this line?
Square root of 8.
Okay. What's another way of saying square root of 8?
Wouldn't that be 4? Oh, yeah.
No, it wouldn't be 4.
Square root of 2. 2 to the third.
Well, it'd be square root of 2 to the third, or you could say it's 2 times the square root of 2. And this can get a little algebraic, so we don't want to get too fixated. What's the length of this line?
Stuart yelled out 4.
Right. And then what about that one? Yeah, it could be 4 times the square root of 2, or the square root of 32. And what are we dealing with here? What's taking place? Anybody want to try to capture what this thing is?
I think we're approaching the Fibonacci series.
Yeah, I think that's probably true. I'm trying to recall the Fibonacci series. Is that always the process of doubling every rotation, every cycle? We can get at the golden mean. That might be a fun one section of a class. But in general, we would call this a logarithmic spiral. Anybody know why we would call it a logarithmic spiral? Anybody have any playful or creative ways of thinking about why we would call this a logarithmic spiral? There's two aspects to it. The logos and the arithmetic. There's 2 parts of this spiral. Anybody have an idea what part the arithmetic might be? Okay. I'm just asking these questions to make sure that I don't... Huh?
The angular rotation.
Okay, right, yeah. And I'm asking them, I mean, people can answer if they know, but I feel better if I ask them, so at least I'm not just, you know, the guy at the whiteboard just talking. So someone said the angular rotation. Every time I get a new length, I've rotated. In this case, does somebody want to say, maybe the person that answered, do you want to tell me what angle I'm rotating by?
45 degrees.
45 degrees, right? So every time I get a new length of a square, I've rotated exactly by 45 degrees each time. And so just like if I'm adding 1, plus 1 is 2, plus 1 is 3, plus 1 is 4, a kind of an arithmetic progression, that's the rotation aspect of this. And we're going to kind of explore this logarithmic spiral next time a little bit more, because there's parts of it that are intrinsic to the Greeks that Archytas uses to define the problem. So then the logos would be that every time I rotate a certain amount, there's a corresponding rate of growth. In this case, I'm always growing by a factor of the square root of 2. If I wanted to say the angle of rotation was 90 degrees, which I could do, then I would grow by a power of 2. I go from 1 to 2, 90 degrees, 2 to 4, and then 4 all the way down would be 8. Now, that's what you would call the geometric side of it. There's a geometric rate of growth. We could even call it exponential. And we'll kind of try to unfold that language, but I'm always careful not to want to jump into kind of algebraic revelry, which can be fun, but can also be distracting. We're not here to kind of become, resilient mathematicians. We want to kind of figure out how the Greek language is working. Now, that's really helpful because it can sometimes map back to what you might be got in mathematics in classrooms and help to provide a basis for way things thought. Like, I'm sure people have seen this, but where does the square root, where does this symbol come from? Well, it's right here, right? So the actual square root symbol comes from the kind of Plato's Meno dialogue of doubling the square. It's there. It was, when I first got that, it was like, damn. You always wonder, well, why did you use that symbol?
Sounds like a conspiracy theory.
Yeah, I know, right? Yeah, it does. It does. But how many even teachers even know what it's just the symbol. In some cases, there are just symbols. If I wanted to say the cube root of 3, they didn't come up with a new symbol. The cube root of 2, they just said, instead of the square root of 2, they put a 2 up, they put a 3 in that same symbol. But at least you know where it's coming from. And that is, we are going to use this cube root of 2. So if that's new to you, then just, well, you'll see, you'll have a better idea of why. Well, this geometric growth process, there's something unique about it in the fact that they call it the logos. And I'll end on this point, but people may have known it because it comes up again, the Gospel of John, the most poetic of Gospels. He starts at the nature of the logos. I was struck in this question of where the Trinity idea had come from. Cusa talks about the Trinity a lot. Where did the notion of the Trinity come from? How was it introduced into Christian theology? Well, it's actually a letter from John. And what is the logos? What is the Trinity? It's the Father, the Logos, and the Holy Spirit. Well, where is this idea of logos coming from? And the language of it, as introduced philosophically, comes from 500 years before Christ. It's something that's not a new notion. It's a concept, it's a language of an idea. It means to gather. It can mean to gather. It can mean to argue. There's different kinds of predicates to it, kind of like the German versammelt. But there's clearly a higher characteristic of a knowability to the physical universe. as you might say, that the underlying characteristics. Heraclitus was the first philosopher to really develop it. And Plato was certainly kind of a Heraclitean in a way. But this notion of the logos, there's a sense of growth. There's a sense of development. And I thought that's just a really interesting characteristic to this process. As a quality of how they thought about something like this. Now, we'll come back to this. Part of this relationship is not simply the squares. But what we're actually dealing with is also a series of triangles. Right, half the square in this case. And they can be different kinds of triangles. But we're going to come back to this next week. So that's pretty much, I think that's an introduction to the course. We'll kind of dive into more of each course. We'll dive a little bit more into the nitty-gritty. But like a good poem, you want to start out a little broad and bring people in. Okay, so I'll leave it there. And if there's any questions or thoughts right now, I can take those, and then we can call it a wrap.
I have a question. Can you hear me?
Yeah, I sure can.
Is this first class going to be archived?
Well, I think if Dave Dubrow hit record on Zoom, then it should be. And then Dave can send it out to the list. He did. So Dave will send it out to the list, and people can watch it if they weren't able to participate.
Great.
Yeah. Okay, any other thoughts or questions or reflections? I mean, I think a lot of this is the basics are pretty straightforward, so.
You told us how to pin your image. Could you go through that one more time?
Say it again.
You told us how to pin your image.
Oh, yeah, sure. So if you go to gallery view on the top right of your screen, so you can see everybody's image, and then you go to my video. The top right of my video has 3 dots. If you click those 3 dots, then you'll see something that can say pin video, something like that.
Okay.
That way you'll always see the whiteboard.
Okay, thanks.
Okay.
Yeah, Michael?
Yeah.
This is a little bit undigested, but I think what Jessica brought up earlier, about how visual space does have this sort of 2 degrees of required to locate any point, and then motion really comes in as a third factor. You want to call it a dimension or factor.
Mm-hmm.
I mean, it's just so, it seems so obvious that anyone who's thinking about space and like the largest expanses of space being the nighttime sky would immediately think about trying to comprehend, the physical universe in that kind of way, as opposed to this Euclidean approach. I mean, it is just so much more intuitive that, I mean, what was the, it seems like any basic understanding of the Greek mathematical works would seem to indicate it as well. I mean, were these were the general works of the Pythagoreans and the early Greek mathematicians buried during the during the Dark Ages, during the Roman times on?
Yeah, I think, I mean, what we largely have are Euclid's Elements, right? Which in some sense was kind of a catalog of all the various geometric proofs. And to that extent, maybe it was useful, even though it wasn't. You know, when you codify language, you can sometimes, you know, the emphasis gets put on the structure and not on the principle of generation. So yeah, I think that like with Archytas, we don't have it. We don't have any proof of Archytas. We just have that the intersection of these three surfaces. I mean, I didn't present that. Maybe I should. Well, you know, I thought about it. Should I present Archytas' proof or not? Now, if you've seen it, you've seen it. If you haven't, it might be even more fun. So, because you're just kind of following the thought. You're looking at it as a scientific challenge. But all we have is the fact that these three surfaces intersect. So to a large extent, it was the quality of thought. And Lynn raises this in a paper that I was struck by, Cusa and Kepler from 2007. Because it's a question of what is revived? What is revived in the Renaissance? You know, cathedral building had already started about 200 years prior to Brunelleschi. So building cathedrals, now building that size of drum for that size of dome, we know was a pretty ambitious Florentine community. But they were building major cathedrals, and in some sense there was a revival already 200 years earlier for the first time of actually reading Aristotle's original writings. So what Lynn says in this paper is that what Cusa helped revive was this quality of thought of the classical Greeks. But he was able to bring that back along with the actual actual writings of Plato. But yeah, I think to a large extent, a lot of the classical Greek material was pulled together later by the kind of that German tradition, right? There was a major investigation of going back to antiquity and exploring now ancient Egypt, ancient Greece, the ancient Roman writings, and beginning to explore and bring that back to the fore. And that's why we now have a lot of this material. I think it was largely lost. And the way of thinking about these questions was largely lost. And we're unique in reviving this. I mean, there is no other institution in the world that is focused on reviving this quality of thought. And to not apply it only to, well, it's obviously applied to education, it should be applied to education as well, but to apply it to the real questions, the greatest challenges we face today. And the fact that we're facing our own pandemic is apropos. Clearly our culture has lost a quality of thought. And this is what we have to revive.
In partial answer to that, there's a quote from Kepler in something in On the Heavens, where he explicitly says, and I'll read it. He says, the Pythagoreans were obscured, quote, on account of the reputation of Aristotle, who rejected this teaching. Although he did not yet fully understand it, this teaching was suppressed, particularly because it was difficult to understand, and it was nearly forgotten over the time of 1,800 years. So, I mean, he explicitly states that the Pythagoreans and the Platonics were suppressed for 1,800 years.
Yeah, that's good.
We should remember that the Romans murdered Archimedes, and then they burned down the library at Alexandria, which had all these ancient writings.
That's right. That's right. And that's when Eratosthenes is recognizing we better get the hell out of here. Sends out a number of explorations out to the far reaches of the Pacific and even and perhaps other places as well.
May I make a comment, sir?
Yeah, sure.
Very interesting discussion. Thank you so much. Very stimulating. You mentioned Brunelleschi. I see that he is sort of a dividing line concerning structural understandings. The cathedrals to that point dealt entirely with compressive continuities, and the vertical loads translated to lateral loads. Naturally, the walls spread when you put something heavy on top of it. And of course, Notre Dame, you've got big trusses and that sort of a structure for the roof. But what Brunelleschi did was freed up the former solution, which was to have flying buttresses, which would transfer that lateral load to the ground. And instead, he captured the load with a tensile ring, an iron ring around the base of the dome. So that is what was so strikingly, breathtakingly beautiful about Brunelleschi's achievement, is that no longer was it necessary to build these great flying buttresses to support that load.
Yeah, right.
It's a sea change in thinking, obviously.
Yeah, no. And much like Einstein, there was a quality of beauty to the space. I mean, Brunelleschi saw the potential for beauty within that higher scientific approach. And it wouldn't be hard to say that the space program today is clearly a part of this process, and what we build as a kind of, infrastructure. I mean, you think of what we're doing right now, but it's very possible that within the course of the next 10 years, certainly within 20, but I would think even sooner, really, within the next 10 years, you could have this class of this kind, but from astronauts on the moon to children in classrooms today. And there's nothing preventing that from happening. That is actually the course of action that we're taking. And that's,
May I make?
think about the power of that quality, and we're talking about a potential major upshift.
Make an additional comment, sir.
Yeah.
That sea change at Brunelleschi, I'd say the next point like that may be R. Buckminster Fuller and his concept of tensegrity, where you have a structure that depends entirely upon tension, shall we say, and the compressives are elegantly suspended in space. It's an interesting thing. I would liken also his arrangement of his tensegrity structures to Mannerist painting, in which you see sight lines directed in various directions from a painting, where they're all contemplating something. It makes Mannerist paintings, that is, following after Michelangelo, so very interesting.
Yeah.
Thank you very much.
This is and there's a lot of interesting things, and this is why it's useful in terms of the course, just so people have a sense of how we want to approach this, is that there's a lot of extrapolations we can make of things. And it can be generally fun and engaging, and to discuss all the various possibilities. But as we approach this, we want to try to keep it's a very narrow path by which to approach this, especially for people that feel less comfortable. People that are more comfortable with mathematics won't find anything very challenging mathematically about it. It's still remarkably provocative in its imagination. But it's very important that we allow people who are approaching this less comfortable with mathematics as a just whatever the cultural factors have been. But because this is totally knowable. It's like learning any language. And the real question is how to get it within the classical Greek mind. And how they thought of these as just an intrinsic way of language, of capturing certain questions. So, okay, any other thoughts or questions right now? Okay. Well, it's nice to have everybody on. Nice to see you. And we'll do this again next week, and we'll take up from the logarithmic spiral. We're going to look at self-similar triangles, just the nature of those, to kind of situate a little bit more how Archytas is going to define the problem. And I guess we'll see how it goes. I might move a little quickly just to see, since we haven't had a chance to have a live audience, which gives me a little bit better sense. But what we might do is plunge into very rapidly how Archytas defines the problem. And then after we get there, kind of unwind it a bit so that it becomes more clear. But that's it. Thanks for coming. Nice to see you. See you next week.
Thanks, Mike.
Yes.
Thank you, Mike.
Thank you.
Bye, guys.
Thank you.
Yeah, thank you.